So this is going to be something of a strategic talk, and I hope you'll be able to take it from the perspective of a strategic talk. DARPA's mission is to pioneer technologies that are going to have a breakthrough impact on national security. And what we've discovered in our history is that things that have a major impact in national security, particularly in the information space, also turn out to be relevant to society at large. So a great example is back when we wanted to have a system that allowed people to communicate together robustly, turned into the internet, when we wanted to be able to cut the costs of building electronic devices, and we funded Mead and Conway and people like that. That led to a lot of the early work in VLSI. We worked with Park to be able to develop new ways to be able to interface with computers. And so the early work in graphical user interfaces and the mouse and so on came out of our work. A GPS turned out to be really important, but it became more and more important to be able to miniaturize it. So we funded the work which said, how do we take GPS from something that fits in the back of a truck to something that you could imagine just having in a single vehicle or even carrying in your hand. 10 years ago, we were working on self-driving cars. We wanted to figure out how you bring together all the various pieces of technology that will allow us to have a car that could do 150 miles across the desert roads of California and Nevada. And there were a couple of competitions that we had in that. The first year, no car succeeded more than about 8 miles in this whole course. The next year, we had this huge breakthrough, and 5 cars got right through to the end. But also in spaces which are more familiar with us, we worked 10 years ago also on voice assistants. So how do you build a voice assistant? We funded SRI, who spun out this little company called Siri that some of you might have heard of, that came directly from the work that we funded. And we've also cared a lot about cybersecurity, and so back in the 90s, we were funding this technique called address space layout randomization to be able to make it much harder for people to break into systems. So we've continued to have an eye on the kinds of technologies that may take 10 years, 20 years to actually get into practice. Though what we're starting to see now with cybersecurity is that as we're working on the technology, the draw from it is, the hunger for it is so strong that we're able to transition it directly from the research into areas of practice. So let's focus on cybersecurity and think about the challenges that we have. You've all seen headlines like this. What I like about this particular set of 3 headlines is that they are quite descriptive of the general mechanisms that are going on in cybersecurity. And for this audience, you're very familiar with this. People are trying to get into our systems to be able to steal information. They're trying to get into do something that system wasn't supposed to be doing. In general, it's the integrity problem. The way I like to think of it more generally is they're trying to have the system do something that they want it to do rather than what you want it to do. Or the disable functionality. We had some great talks earlier today about the challenges of disabling functionality. But rarely does a cyber attacker get straight in and do one of these things. More often, they're trying to do secondary tasks so that later on they will be able to do their primary task. So they're trying to get in and hide so that you don't notice them, or persist, or communicate back to base in a way that you don't notice, or take a place on the system and be able to move to another system. And with this sort of complexity of what a cyber attack is trying to do, we find that one challenge that we face is that there's a lot of what I like to call one-dimensional thinking about cyber that we experience in various communities that we talk to. And so to try and break out of that notion of cyber is all about this one thing or this other thing, I like to walk through a fairly simple example. Suppose somebody wants to get a keylogger on your machine, maybe just to steal your credit card or something like that. They might not be able to just install that application, and so what they might do is exploit some vulnerability, perhaps in Flash or some other mechanism, where when they find the vulnerability, they can feed some code in and install it. So now the question is, how do they get that Flash to run? Well, maybe they craft a web page that you go and visit, and when you visit it, there's a Flash ad that when it runs, then that opens up the channel that allows the exploit to be installed. And so now how do you get them to visit the web page? Well, you send the user an email which has a particular link and so on. And we often get told in the DoD and elsewhere, don't click on links. And to some extent, that's a ridiculous piece of advice, because the idea of saying don't click on a link when the whole of the internet is designed around links is just ludicrous. In fact, sometimes it happens that we have a phishing exercise that takes place to see which of us fall into the trap of clicking on links. And then a week later, we get a report which says 97% of you did fine, but 3% of you clicked on the links. If you want more detail, see the attached PDF. And they kind of don't get the irony in that. So if you take a complex situation like this, I like to think of it in terms of various quadrants so that you can recognize that activities are taking place in different parts of the cyber ecosystem, as it were. So are we talking about a challenge that is facing the user of a system, or are we talking about the applications that are actually loaded on the system? And when I talk about applications, I don't just mean App Store kind of applications on your phone, I mean more generally. Or are we talking about the way that that software is implemented and the flaws in that software? Or are we talking about some foundational infrastructure that system is trying to rely on in what it's working on? And so I think it's really useful to think of these dimensions of attack. And indeed, in each of these dimensions, you can find attacks that only rely on a single one of those dimensions. So it may be that somebody has stolen your credentials and can pretend that they're you and take all of your, take rights as if they were you. Maybe steal your information or act as if they were you. Or it may be that you're induced by the excitement of this free software to put it on your platform, and there's some hidden functionality within there that now starts behaving as if it's you on your platform. Down at the implementation layer, where a lot of things we talk about can go wrong, buffer overrun is a classic, many other things can take place there. But even down in the network itself or in the hardware, there are many kinds of risks that can take place. So there's lots of challenges here. Now, when you even just think about one platform, so we work with physical systems quite a lot, helicopters, things like that. Even just one platform, like a simple helicopter like this, actually has a really complicated cyber story once you start peeling it back. First of all, there's the hardware and the software that's on that system in the first instance. So where did that hardware come from? Where did that software come from? Are there vulnerabilities in the hardware or the software as the thing got built? Now that machine is unlikely just to be flying in isolation. It's going to be connected with maybe it's got GPS radios and it's got signals coming from the sky that have the potential to be spoofed. It's got ground station commands coming in. Maybe the system doesn't get attacked. Maybe it's the ground station that gets attacked and now the wrong commands are being given to it and so it goes off to the wrong place. And then when you start thinking about the whole issue of upgrades, when I want to put new software on that, how much can I trust the systems that are being used to do the upgrade? So you suddenly start seeing this whole complex ecosystem of things that make it, at the first instance, almost impossible to do anything interesting in cybersecurity in this kind of space. But actually, it's not all bad. When DARPA was really engaged from about 5 years ago in cybersecurity, there was a bit of a sense in society at that time that we had this flood of stuff coming against us, and what on earth are we going to do about it? And I think what we've seen, again, in society, but also in technology that we and others have generated, is that we're now kind of in the fight, in the cyber fight. And it's not that we're just defenseless against all of this stuff coming against us. And so the way I like to challenge my office is to say, okay, so we're in the fight. What would it take to win at cyber? If you not just be able to solve everything necessarily, but just to be able to win at cyber. Can we make it so hard to break into a system, for example, that you would have to be a nation state to be able to play at this game? That would be a great thing to be able to consider. And indeed, we see a lot of technology in common use now that has having a huge impact. At the user level, things like two-factor authentication, again, a great talk earlier about the value of some of those things. But also inside a threat to see to what extent is the user the actual problem within the system that you're dealing with. The kind of thing that we see with the iPhone, where you can only get signed software running on it, turns out to wipe out whole classes of malware, and it's been tremendously effective there. Within the implementation layer itself, when we think about how we harden an implementation, there's lots of techniques to be able to protect memory so that you can't just push across the end of a buffer and be able to take advantage of something. And then down in the underlying infrastructure, many great opportunities there. Not to say that there's not huge problems in all of these other spaces, but we're definitely in the fight, and we're definitely starting to make progress. So now, what would it take to win at cyber? What are the kind of thrusts that we would like to do? And so we see at DARPA that it's worth pushing in 3 different areas. The first is a kind of traditional way of thinking about security. What would it take to harden the systems that we have to make it harder for people to get in with a cyber attack? So you can think of that like built-in security. Another one of them is when we're working with systems, there's almost certainly going to be various insecurities that we have to deal with. How do you get your job done? How do you succeed at your mission, even when there are those insecurities? So can we manage the insecurity? Can we operate right through the midst of insecurity and still get the job done? And then both of those are really focusing on how do I focus on getting my job done and not have to worry about cyber sort of front and center of my mind. And the third is, let's suppose cyber is the domain that is your job, that front and center, you now need to think about that. What will it take to actually win in the cyber domain, particularly perhaps at a national level when you may be facing peer adversaries? So I'd like to give you 2 examples of programs in each of these areas, just to give you a flavor of the kinds of things. Actually, we've got about 8 programs in each of these areas, so this will just give you a slight flavor. The first I like to talk about is cyber retrofit, and this is using formally verified software to make the systems much more robust than they were before. Now, we know we can't sprinkle security on an existing system, but in a similar way, you can't sprinkle earthquake protection on a building. But that doesn't mean you have to knock the building down and start again. Here in California, there's a whole industry which does seismic retrofit. And what you do, you jack up the building, you put in a new foundation underneath it, and new structural elements, and then you reattach the building to that. And now it's much more robust than it ever was before. And so we did that last year with a helicopter. In fact, 18 months ago, with a helicopter. We took the mission computer, we jacked it up, we put a formally verified microkernel underneath it, we put some formally verified communication software on it, and then we reattached the yellow pieces were the original pieces of software, including a camera application that connected out to Wi-Fi and a physical camera, so a number of drivers. And then we said to the red team, can you break into this system at all? And they were unable to break in. And so we said, let's make it more interesting. Suppose we give you a foothold. We'll give you root on that Linux. Now, from having root on that Linux on the mission computer, how bad can you get it? And they were unable to break. They were obviously able to destroy that camera application and everything in that partition, but they were unable to pivot from that to leverage further. So that's an example of a cyber retrofit, and we're trying to scale that up. Another great example, this was last summer, the Cyber Grand Challenge. What we did there is we wanted automated systems to play cyber capture the flag against one another. And we have leaders of 2 of the winning teams here on the front bench. So this is a community that cares a lot about this. Let me tell you one story. There was a case where there was a bug that we'd seeded a lot of bugs initially, but there was some bugs that we didn't know about that had got there just because human beings wrote this code. One of the cyber reasoning systems found a bug, we didn't know about it. They found an exploit, they launched it against another party and succeeded in stealing data from that other party. A third computer saw that attack taking place, reverse engineered that attack, figured out what the vulnerability was, constructed a patch for that, and applied it to their own system so that they would be invulnerable. This whole thing took 20 minutes, and that was a game changer. When we think about operating through, we've got a lot of systems that are already built. We may only have the binaries. So a good question is, can we do something with binary diversity to make them much more resilient than they were before? And so we may take the original code, and then what we do is produce another variant of the whole system with checkpoints, like safety checkpoints. But the binary, represented by the gray and white dots at the top, is laid out differently. Maybe the first one had the stack growing upwards, and we've got a new version which now has the stack growing downwards and has all the pieces in different places and changes some variables and all sorts of things like that. And now if there's an attack that was designed against that first binary, it may succeed, but it may then produce a crash or garbage in the second binary, and we'll be able to detect that problem and do something about it. And so there's a lot of interest in being able to harden systems like this, just so that we may not fix the problem, but at least we know that there was a problem, and we may then be able to go back to a safe state. Another thing that we're interested in is being able to use the internet and networks that we don't control to be able to do mission. But so maybe we've got a mission server and a mission client, and there's communication going between there, but perhaps the adversary gets somewhere on the middle of that network outside of our control, and maybe we've got an encrypted tunnel through that, so we can't even look at what's going on that network, because that would violate our encryption boundaries. But we now know that something is going wrong. Perhaps all the data is being ripped out of the packets or something like that. So what we want to be able to do is within milliseconds notice that something has gone wrong and be able to construct alternative paths to neighboring edge points. So I may not be able to communicate with you, but I've got a buddy over there, and I communicate with my buddy, and that buddy communicates with you. And the adversary who is in the way and interfering with the original flow now isn't able to interfere with this revised flow. And so these are two examples of how we think about being able to operate even in the presence of insecurity. And then when we think about cyber as a domain in its own right, where we want to be able to do mission, we've got a large program called Plan X, which looks at the question of what does it mean to have operational viewpoint or cyber intelligence of the whole of the cyber domain. We're used to, we're very familiar in the DoD with being able to see what's going on the oceans or see what's going on land and be able to make sensible choices when we see that. But what's going on in the cyber domain? Has a country gone offline? Has a company gone offline? Has something significant been reconfigured? Is traffic being reconfigured? And so what we're doing is being able to build the ability to, first of all, observe and know what's going on global networks so that we can understand that kind of domain that we're needing to operate in. And not only being able to see what's going on at the level of grand networks, but what we'd love to be able to do, and in fact we've made huge progress there, is be able to have a very detailed model. So if I said that we had a graph of a network, you might think I have a computer here and another computer here and maybe an internet service provider or autonomous system or something like that connecting them. But what we're very interested in being able to do is say, I've got this version of the software running on this version of an operating system, which is running on this virtualization environment, which is running on this platform, which has this Ethernet card, which now connects through this Ethernet to this switch, which is running this software, which is now connected to those other things, and that level of detailed model so that we can really see in great detail the various places on our network where malware might be hiding, where we may have to do something about it. So Plan X has that large graph being built. It may be just of an enterprise system, or it may be some version of it, even the visible part of the internet, to be able to see the structure. And then we can say, if I take systems that have the following kind of configuration, and I want to turn them into systems that have this other kind of configuration, how do I construct, at a very high level, the plan to make that happen? So a very exciting sort of command and control for network operations. Also thinking about networks, we very much care about network flows and what's happening. And there's a lot of work being done which say, if something violates this rule, it's a problem, or if something violates that rule, it's a problem. But that's like old-style AI, where you've got handcrafted knowledge. We're much more interested in using the manifold structure of data to be able to see things in time series and in data shapes that indicate whether something is normal or not normal. And so here's an example where we were able to find a time series thing that was anomalous and indicated a problem. So here's the three thrusts that we have: harden systems against cyber attack, operate through cyber attacks, and win in the cyber domain. And I think we're at the stage that we have lots and lots of technology, and the challenge now is figuring out what are the market forces and other drivers that interfere with us being able to put it into practice. Thanks very much.